Swayam Prabha. Digital India. Educated India.
Welcome to lecture 23rd of the topic on time series analysis and forecasting. In this lecture, we will discuss some of the methods of time series forecasting. Forecasting is one of the main objectives of time series analysis. It plays a very important role in various fields. For example, in stock market, if you can forecast the share price of some company, then of course you can gain a lot of money. Government requires forecasting in various fields like population projection, or you can in medical field, if you can forecast the outbreak of some disease, then accordingly you can plan the things, you can plan the number of beds in the hospital, etc. So, it plays a very important role in different fields. In financial market also it plays a very important role. You can forecast in marketing, if you can forecast the demand of certain commodity, then accordingly you can plan your logistics, you can plan your manufacturing process, etc. In one of our earlier lecture, in lecture 7, we discussed different adaptive forecasting procedures. Those procedures were based on smoothing, time series smoothing, different smoothing procedures. In fact, we discussed 3 smoothing procedures for forecasting purpose. One, the first procedure, which was based on single smoothing, it was used when your time series does not have any trend or the seasonal component. So, and if your time series has trend component, then you can use the second method, which we discussed in that lecture, lecture 7. That procedure was 2-stage smoothing procedure. We use a smoothing in 2 stages. And if your time series has both trend and seasonality, then you add one more stage, you use a 3-stage smoothing procedure to take care of both trend and seasonality. That procedure, adaptive forecasting procedure, was based on the variation present in the time series, means whether your time series has a trend component or it has both trend or seasonal component, or it does not have any of these 2 components. So, your procedure depends upon the presence of these variations in your time series. Accordingly, you have to select the proper procedure. Now, one of the drawback of that procedure was it does not take into account the auto-correlation structure of the observations, how the observations are related with the past observations. It does not take care of this phenomena. In Box-Jenkins approach, we develop different models keeping in view how the observations are related with the past observations, how the present observation is affected by the past observations and the shocks related with the past observations. So, accordingly we choose the model, we choose either autoregressive model when your present observation is directly affected by the past observations, but it is not affected by the shocks related with the past observations, then we choose autoregressive model. Then we have moving average model when your present observation is directly affected by the shocks related with the past observations, not by the past observations directly, but by the shocks related with the past observations. Or when your observation, the current observation is affected by both the past observations as well as the shocks related with the past observations, then we go for ARMA models. Now, you can also develop forecasting procedure based on these Box-Jenkins model. The beauty of Box-Jenkins model is that these models take care of the relation or the autocorrelation structure between the present observation and the past observations. Similarly, the forecast based on Box-Jenkins models also take care of the autocorrelation structure between the information or the observations and shocks available up to the current time period and the future observations which you have to forecast. So, that is the beauty of forecast based on Box-Jenkins procedure. Then of course, if you are forecasting the future observation, then you require some criterion also for checking whether your forecast is good or not. So, one of the criterion is forecast error, and then forecast error is sometimes positive, sometimes it is negative. So, to obtain an absolute measure of forecast, magnitude of forecast, we take forecast mean squared error, and then we try to develop forecast which minimizes that forecast mean squared error. So, now I come to the main topic. Forecasting is frequently made in various fields to guide decisions. In whether you daily find rain forecast or temperature forecast. So, in weather it plays very important role in taking various decisions, and then in marketing decisions, if you can forecast the price of certain commodity, or it also helps you in deciding the price of a commodity, or supply chain decisions. If you know that in a particular area there is more demand of certain commodities, in North India there is more demand of winter clothes during December and January, or in November also, then accordingly you can plan your supply chain. Then it also helps you in making advertising expenditures related decisions. So, means for the taking decisions regarding the advertising expenditure, you have to take care of, or you have to forecast the responses of the sales of, means whatever commodity you are interested in the sales of that commodity, you have to take responses of the customers to different marketing strategies. So, it helps you, forecasting helps you in marketing, taking many marketing decisions. Then forecasting sales of business firms. So, if you are able to forecast the sales of business firms, then it helps you in making decision in the inventory management, It also helps you in sales management, how to manage your sales, or production planning, and in which period you have to focus on more production and in which period you can reduce your production. So, this kind of decisions help you if you are able to forecast the sales. It also helps you in strategic planning regarding product lines. So, in business firms it helps you in many ways. Revenue forecasts. Revenue forecasts also play a crucial role in planning expenditure in budgeting process. So, in making your budget, it helps you. Then forecasting economic variables such as GDP, unemployment rate, consumption expenditure, investment, price level and interest rate. So, all these are economic variables, and if you are able to forecast these economic variables, it helps you in taking decisions regarding monetary and fiscal policies controlled by the government. Means if you observe that accordingly RBI decides the repo rate, reverse repo rate, etc. So, population forecasting. Population forecasting helps you in planning government expenditure on health care. So, then it also helps the government in deciding infrastructure expenditure. Say after 5 years, how many houses will be required in a particular city? Population is increasing, and if you are able to forecast the population, then you can decide or how many electricity consumption will be there after 5 years or after 10 years or after 15 years. Social insurance, anti-poverty programs and so forth. So, again population forecast is helpful in different government plannings. Accordingly, government can plan its expenditure in various fields. Basically, the objective of the forecasting is to predict the future value of a time series based on the data collected to the present. So, you have the information up to the present, and then you have to predict the future value of the time series. That future value may be, say, for the next time period, means if you have yearly data, then it may be the next year. You have information up to the current year, and then you want to predict the value of the time series for the next year, or you want to predict what will be the value of the time series after 5 years. Or if you are doing weather forecasting, you may be interested in forecasting the rainfall after 1 week or next day rainfall. So, basically you want to predict the future value of the time series, and then you have the information up to the current, and by utilizing that information you want to predict the future value. Given a stationary or invertible data generating process and the information up to time t, say ft, you have the information up to time t. So, you are presently at time t, and this ft denotes the information up to time t. You also assume that your data generating process is stationary and invertible, and then you want to obtain h step ahead forecast. Means suppose you have the time series up to the present, say you are at time t. So, you have observations y 1, y 2, y t. So, this information constitutes your f t, and you want to forecast h step ahead value, means you want to predict the value of y t plus h, and then with a linear prediction function, means for predicting the value of y t plus h, you make use of a linear function of y 1, y 2, y t. Then this time index t is called the forecast origin. You have information up to time t. So, this is the forecast origin, and means you are here. So, you have information up to this point. And then you want to predict any of these values, say t plus 1, t plus 2, so on. You have t plus h here. So, this is your origin. From here to here means y t plus 1. If you want to predict the value of y t plus 1, then this is your one step ahead forecast. If you want to predict the value of y t plus 2, then this is your 2 step ahead forecast, and if you want to predict the value of y at this time point, say y t plus h, then the forecast is called h step ahead forecast. So, this t is the forecast origin, and this positive integer h is the forecast origin. And suppose y curl t h is the h step ahead forecast of y t plus h at the forecast origin t. You have information up to time t, and then you have to forecast the value of y t plus h, and suppose this h step ahead forecast is y curl t h. Now, we try to find out the best linear predictor. We write these n observations y 1, y 2, y n in this vector form. This y within bracket n is equal to y n minus 1. Of course, we have written all these observations in reverse order. So, y n minus 1, so on y 1 transpose. So, this is actually n cross 1 vector. So, this y n is the vector of n observations on time series. Then y n plus h is the future value to be predicted. So, since you have n observations on the time series, so your origin for forecasting is n, and y n plus h is the future value to be predicted, h equal to 1 to so on. So, this h is the origin, and we assume that your predicted value is a linear function of y 1, y 2, y n. So, basically we are concentrating on obtaining the best linear unbiased best linear predictor. So, we have considered a linear function of y1, y2, yn for predicting the value of yn plus h. Then you can write it as these beta naught, beta 1, so on beta n are the weights assigned to, means beta naught is something like intercept term, beta 1 is the weight assigned to yn, beta 2 is the weight assigned to yn minus 1 and so on, beta n is the weight assigned to y1, and then you can write it as beta naught plus summation j equal to 1 to n beta j yn plus 1 minus j. So, for j equal to 1 you get yn here. So, beta 1 yn the first term, for j equal to 2 you get beta 2 yn minus 1 and so on. For beta for j equal to n you get beta n yn plus n 1 minus n. So, you get y1, the last term. Now, this y curl n h is the best linear predictor if it minimizes the prediction mean squared error. How we define the prediction mean squared error? This is the actual value of y at time point n plus h, yn plus h, and this one is the predicted value of y n plus h using the observations y1, y2, yn. So, we subtract this predicted value from the actual value. This is actually equal to yn plus h minus y curl n h whole square. So, for obtaining the best linear predictor, we are using the criterion prediction mean squared error. This is the prediction error, and then you have taken expectation of square of this prediction error. And then we try to find out the values of beta naught, beta 1, beta 2, so on beta n by minimizing this prediction mean squared error. And for minimizing this SB, how we proceed? We differentiate it with respect to beta naught. So, if we differentiate SB with respect to beta naught, then you get 2 times expectation of yn plus h minus beta naught minus summation beta j yn plus 1 minus j, and then you have minus sign here. So, you get minus sign here, and you substitute it equal to 0. And then you take this minus 2 towards the right hand side. Expectation of yn plus h is equal to mu minus expectation of beta naught is beta naught minus expectation of each of these y's yn plus 1 minus j is again mu, because you have already assumed that the process is a stationary process. Remember, initially we have assumed that your time series process is stationary as well as invertible. So, all the y's have same mean. So, expectation of each of these y n plus 1 minus j is equal to mu. So, you get mu times summation j beta j equal to 0. You get this first equation. Now, this gives beta naught equal to mu into 1 minus summation j equal to 1 to n beta j. Then, in the expression for S b, we substitute beta naught equal to mu into 1 minus summation beta j. So, if we substitute the value of beta naught here, then you get y n plus h minus mu. Then you have minus here summation j equal to 1 to n beta j y n plus 1 minus j, and then you get minus beta j you can take common. So, you get minus mu. So, means you get this term summation j equal to 1 to n beta j y n plus 1 minus j minus mu whole square. So, you get this value of S b after substituting the value of beta naught in the expression for S b. Then we differentiate this expression for S b with respect to beta I, say. And when we differentiate it with respect to beta I, then again you obtain minus sign you get from here minus 2 times expectation of y n plus h minus mu minus summation j beta j y n plus 1 minus j minus mu. Then corresponding to ith term, you get if you differentiate with respect to beta I, then corresponding to the ith term, what you get here? You get y n plus 1 minus I minus mu. So, this into this equal to 0. You also get minus 2 here, but you can take minus 2 towards the right hand side. Now, if you multiply these two quantities and take expectation, then expectation of y n plus h minus mu into y n plus 1 minus I minus mu, this is equal to gamma, and then you have lag n plus h minus n minus 1 plus I. So, ultimately you get gamma h plus I minus 1, this n will cancel out. And what you get here, when you multiply y n plus 1 minus j minus mu by y n plus 1 minus I minus mu, and then you take expectation, you get gamma n plus 1 minus j minus n minus 1 plus I. So, you get I minus j. So, finally, you can write this equation in the form gamma h plus I minus 1 equal to summation j equal to 1 to n beta j gamma I minus j. So, you get this expression, or this expression, and I varies from 1 to n. Now, suppose we slightly change the notation, we write beta j equal to phi n j h. Then beta naught is equal to phi n naught h is equal to mu into 1 minus summation j equal to 1 to n phi n j h. Then for the I equal to 1, what you get? If you take I equal to 1, you get gamma h equal to summation j equal to 1 to n beta j. You have I equal to 1. So, 1 minus j, or you can take j minus 1 also. So, you get gamma h equal to, then we write betas in terms of phi's. So, phi n 1 h, the first term is gamma naught plus phi n 2 h plus so on phi n n h gamma n minus 1. Again for I equal to 2, you obtain gamma h plus 1 equal to phi n 1 h gamma 1 plus phi n 2 h gamma 2 plus 1 phi n n h gamma n minus 2, and so on. So, substituting the values of I in this equation 3, finally, you write I equal to n, you obtain all these equations. Then solving these prediction equations, you can obtain the values of phi's. Now, suppose we assume that mu is equal to 0, then obviously this implies that phi n naught h is equal to 0. Now, suppose you take h equal to 1. H equal to 1 means you are obtaining one step ahead forecast, means one step ahead forecast is y curl n 1, h is equal to 1. Then for h equal to 1, you write the coefficients as phi n 0 1, phi n 1 1, and so on. Then we write this vector, we define this vector phi n 1 as phi n 1 1, so on phi n n 1 transpose. So, this is n cross 1 vector, and we define this vector gamma n 1 as gamma 1, gamma 2 up to gamma n. So, this is the vector of these auto covariances. This is also n cross 1 vector. Then we define n cross n matrix gamma n with elements gamma naught, gamma 1, so on gamma n minus 1. These are the elements of first row. The elements of second row are gamma 1. After that, you have gamma 0, then again gamma 1. up to gamma n minus 2 and so on, gamma n minus 1, gamma n minus 2 and so on up to gamma naught. So, this is your n cross n matrix capital gamma n. Then for h equal to 1, you can write this equation 3 as gamma n. In matrix notations, you can write all the equations in 3 as gamma n phi n 1 equal to gamma n 1 is this is the set of equations 3, and you are writing these equations in matrix notations, and you have taken h equal to 1. So, you get gamma 1, gamma 2 so on, you go up to gamma n. And actually this matrix gamma n is non-singular matrix, because gamma naught is greater than 0 and gamma h tends to 0 as h tends to infinity. Your process is a stationary process. So, these autocovariances tend to 0 as h tends to infinity. So, you can always define inverse of gamma n. So, phi n 1 is equal to gamma n inverse gamma n 1. So, one step ahead forecast value is phi n 1 transpose y n equal to gamma n 1 transpose capital gamma n inverse y n. Then you can easily obtain the expectation of y n plus 1 minus y n curl 1 whole square. If you take a square of this, then expectation of y n plus 1 square is equal to gamma naught. Expectation of a square of this quantity this is equal to, you take a square of this. So, gamma n 1 transpose, then you take expectation of y n and then you write y n transpose here, again gamma n inverse and gamma n 1. And expectation of this quantity is gamma n. So, you get gamma n 1 transpose, gamma n inverse, gamma n inverse, gamma n 1. So, you get this quantity, and then you have cross product term minus 2 times expectation of y n plus 1, and then you write the value of this, and then in expectation you just take y n plus 1 here, and ultimately you obtain expectation of y n plus 1 is equal to gamma n 1. So, you get minus 2 times this term. So, finally, you obtain this term. So, this is prediction mean squared error for one step ahead forecast. In general, for h step ahead forecast, y curl n h is equal to say phi n h transpose y n, and this is equal to gamma n h transpose y n capital gamma n inverse y n, and h step ahead prediction mean squared error is equal to gamma naught minus gamma n h transpose capital gamma n inverse gamma n h. So, just like the one step ahead forecast, you can obtain this h step ahead forecast also and its prediction mean squared error. We have gamma n h is equal to gamma h plus 1, so on gamma n plus h minus 1. So, here you are starting from gamma h, and phi n h is equal to phi n 1 h, phi n 2 h, and so on phi n n h transpose. So, this is how you can obtain h step ahead forecast and its corresponding prediction mean squared error. Now, we consider the AR2 process as a special case. So, for AR2 process, y t equal to phi 1 y t minus 1 plus y 2 y t minus 2 plus u t. You have one step ahead forecast equal to phi 1 1 1 y 1, where phi 1 1 1 is equal to gamma 1 upon gamma naught. Say, what is the formula for phi? This is the formula for phi. So, for the AR1 process, you get gamma 1 here, for n equal to 1 you get gamma 1, and here you obtain, instead of gamma n inverse you get gamma naught, and this is equal to rho 1. Now, suppose you have two observations and you want to predict y 3. So, you have y 2 curl 1 is equal to phi 2 1 y 2 plus phi 2 2 1 y 1. Again, you can obtain this vector as, we apply the same formula, gamma n inverse is equal to n is equal to 2. So, gamma naught gamma 1 gamma 1 gamma naught whole inverse, and here you have gamma 1 gamma 2, and then you just take inverse of this 2 by 2 matrix, which is very simple, and finally you obtain this quantity. Means just write these auto covariances as auto correlation coefficients. So, from here you can obtain the values of phi 2 1 1 and phi 2 2 phi 2 2 1 also. So, phi 2 1 1 is equal to rho 1 1 minus rho 2 upon 1 minus rho 1 square, and phi 2 2 1 is equal to this. Now, remember in the relationships between phi 1 and phi 2 and the corresponding autocorrelation functions in AR2 process. In AR2 process, this is your phi 1 and this is your phi 2. So, phi 2 1 1 is equal to phi 1 and phi 2 2 1 is equal to phi 2. So, this is how you can proceed for prediction in AR2 process. For forecasting in a stationary ARMA process, so suppose this is your h step ahead forecast. Again, you use the minimum mean squared error loss function or minimum mean squared error criterion. So, we minimize y curl t h minus y t plus h square given the information up to time t f t. So, suppose g t h is any other linear forecast, then the mean squared error of this y curl t h should be less than g t h, or you can say y curl t h is the forecast which minimizes this prediction mean squared error. Now, using the wall decomposition, you can write y t in this form, nu plus summation I equal to 0 to infinity theta I u t minus I. Then y t plus h is equal to mu plus summation I equal to 0 to infinity theta I. You just replace this t by t plus h. Now, given the information up to time t, we assume the following representation for the linear prediction function. So, y curl t h is equal to mu plus summation I equal to 0 to infinity. Say you are taking the coefficients theta I h u t minus I. So, this is the predicted value of y t plus h using the information up to time t, and you have to obtain the values of these coefficients. Then forecast error or h step ahead forecast error is f t h equal to y t plus h minus y curl t h. And then for obtaining the values of theta I h, you have to minimize expected value of f t h square or mean squared prediction error, which is equal to expectation of y t plus h minus y t curl h whole square. Then we substitute the values of y t plus h and the h step ahead forecast here. Then we collect the terms corresponding to different UTs or UT plus h. For I equal to 0, you get a term in having UT plus h. Theta I equal to 0 means theta 0, which is 1, UT plus h, plus for I equal to 1, you have theta 1 UT plus h minus 1, so on. You go up to I equal to h minus 1. So, theta h minus 1 ut plus 1. Now, after then for I equal to h, you get a term theta h ut here, and in the second term for I equal to 0, you get theta 0 h ut. So, we combine these two terms, both the terms have ut common. So, for k equal to 0, you get t here. For k equal to 0, you get theta h minus theta 0 h ut here. Similarly, for k equal to 1, you get theta h plus 1 minus theta 1 h ut minus 1 here, and this term you get by combining these two terms for I equal to h plus 1 and I equal to 1, and so on. So, finally, you get this expression, and then we take a square of this and then expectation. So, obviously, the expectation of all the cross product terms are equal to 0. So, we just focus on the square terms only. So, expectation of square of this term is sigma square u, then you have square of this term theta 1 square, expectation of square of this term is again sigma square u, and so on. So, you get 1 plus theta 1 square, so on theta h minus 1 square sigma square u plus sigma square u into summation k equal to 0 to infinity theta h plus k minus theta k h square. And then your objective is to minimize this quantity, or you have to obtain the values of theta k h in such a manner that this is minimum. Now, you do not have to bother about this term, because this term does not contain theta k h, and this term is minimum when theta k h is equal to theta h plus k. For all k equal to 0, 1, so on. So, the optimum prediction function is now this. You just substitute the values of theta I h here. So, you get this optimum prediction function for h step ahead forecast. Again, expectation of ut plus h given ut minus 1, so on. This is equal to ut plus s for s less than or equal to 0. For if s is negative, then what you get here, say for example, if you take s equal to minus 1, then you get expectation of u t minus 1 given u t minus 1, and expectation of any random variable x given x is obviously equal to x. So, you get u t plus s if s is less than or equal to 0, and it is 0 for s greater than 0. So, expectation of y t plus h given u t minus 1 so on is mu plus summation I equal to 0 to infinity theta I plus h u t minus I. And then this expectation of y t plus h is the same as this term. So, actually this shows that the optimum h step ahead prediction function is expectation of y t plus h given f t. So, now your problem is very simple. For obtaining the optimum prediction function for any stationary process, stationary ALMA process, you simply obtain expectation of y t plus h given f t. Then your forecast error is f t h is equal to f t plus h minus f curl t h, and this is actually equal to, just substitute the values of y t plus h and y curl t h, then you obtain u t plus h plus theta 1 u t plus h minus 1 plus 1 plus theta h minus 1 u t plus 1. And if you take expectation of this forecast error given u t minus 1 so on, means given the information up to time t, then expectation of this forecast error is equal to 0. Means this y t curl h is an unbiased forecast of y t plus h. So, the forecast expectation of y t plus h given f t, it not only minimizes the mean squared prediction error, it is also an unbiased forecast. So, we conclude that the best linear unbiased predictor of stationary ALMA processes are given by the conditional expectation of y t plus h given the information up to time t. For one step ahead forecast error y f t 1 equal to u t plus 1, we have expectation of f t 1 equal to expectation of u t plus 1 equal to 0, and expectation of f t 1 give f s 1 is equal to sigma square u for all t equal to s, and it is 0 for t not equal to s. So, actually f t 1 is a purely random process. This prediction error is a purely random process. For h step ahead forecast, f t h is equal to u t plus h plus theta 1 u t plus h minus 1 so on plus theta h minus 1 u t plus 1. Again this f t h is just like an m a h minus 1 process, its expectation is 0 and variance is equal to 1 plus theta 1 square so on plus theta h minus 1 square sigma square u. So, again this h step ahead forecast or error of h step ahead forecast also has expectation 0, and this variance of f t h can be used to construct confidence interval for h step ahead forecast, because for constructing the confidence interval you also require the variance of the h step ahead forecast. So, using it you can construct the confidence interval also. Again you observe that variance of f t h is this 1 plus theta 1 square, so on theta h minus 1 square, sigma square u, variance of f t h minus 1, then you go up to theta h minus 2 square. And then you can easily verify that variance of f t h minus 1 is less than or equal to variance of f t h. And this is quite obvious also, this is logical also, because nearby observations at nearby time points predicted more accurately. Again, if you take limit h tending to infinity, then y hat t h tends to mu, means expectation of y t. And if you take limit h tending to infinity, then variance of f t h tends to sigma square u summation j equal to 0 to infinity theta j square, or this is equal to variance of y t. So, if you are forecasting at a very long horizon, you can say, for a very large value of h, then your forecast becomes the mean of the process, and variance of the forecast value is same as the variance of y t. So, variance of y t plus h is equal to this, variance of y equal t h is, we have already derived it, this is equal to sigma square u summation j equal to h to infinity theta j square, and variance of f t h is equal to sigma square u summation j equal to 0 to h minus 1 theta j square. Now, you can easily verify that variance of y t plus h is equal to variance of y hat t h plus variance of f t h. So, basically variance of y t plus h has been decomposed into two variances, the variance of h step ahead predicted value and the variance of h step ahead prediction error. So, here I am going to stop. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.